Imagine the universe as a grand cosmic dance. Everything follows a set of rules. Planets orbit stars. Stars gather into magnificent galaxies. And for centuries we thought we knew the choreographer. His name was Isaac Newton. His laws of gravity describe the waltz of the planets around our sun with breathtaking precision. These laws are simple but powerful. They tell us that the closer an object is to the center of gravity, the faster it must move to stay in orbit. The farther away it is, the slower it can afford to go. This elegant logic was the bedrock of our understanding of how things moved in space, a universal truth we held dear. We see this principle play out right here in our own cosmic neighborhood, the solar system. Mercury, the planet closest to the sun, zips around its star at a blistering pace. It has to. The sun's immense gravitational pull is strongest there, and Mercury must maintain its high speed to avoid being swallowed whole. Far out in the cold, distant reaches of the solar system, Neptune ambles along on its journey. It moves much more slowly than Mercury because the sun's gravitational grip is far weaker at that distance. This relationship between distance and speed seems so fundamental, so universal, that we naturally expected it to apply everywhere, even in the sprawling star cities we call galaxies. But the universe, it turns out, had a surprise for us, a big one. The galaxies were not behaving, they were spinning too fast. In the 1970s, an astronomer named Vera Rubin, Kent Ford, decided to put this simple prediction to the test. They weren't looking to start a revolution, they were just doing good, careful science. Using powerful spectrographs, they meticulously measured the speed of stars' gas clouds at various distances from the center of the Andromeda Galaxy, our closest spiral neighbor. They pointed their instruments at the bright, bustling core, then systematically moved outwards to the faint, lonely arms spiraling into intergalactic blackness. They were charting the galaxy's rotation curve, a graph that plots orbital speed against distance from the center. What they expected to see was a curve that rose sharply near the center, then fell off gently toward the edge, but that is not what they found. Not at all. The stars near the center moved quickly, just as predicted, but farther out, the speeds didn't drop. The stars on the very edge were moving just as fast as the stars closer in. This was bizarre, like a merry-go-round where outer horses keep pace with inner horses. It made no sense. To hold those outer stars in orbit required colossal gravity. This wasn't just a fluke in Andromeda. Scientists named it dark matter. Vera Rubin's observations revealed a ghost in the cosmic machine. The strange rotation of galaxies was the first major clue, the smoking gun that pointed to a hidden cosmic component. But in science, one piece of evidence is never enough. You need to build a case. You need corroboration from independent lines of inquiry. Evidence began pouring in from all corners of the cosmos. One of the most spectacular confirmations came from gravitational lensing. Einstein predicted massive objects bend space-time. They act like a lens that distorts and magnifies light. Astronomers pointed telescopes at massive galaxy clusters. They saw background galaxies warped into strange arcs and multiple images. By measuring that distortion, scientists calculated the cluster's total mass. The result was astonishing. The mystery deepened when we measured cluster velocities. Galaxies orbit a cluster's center of mass. In the 1930s, Fritz Zwicky noticed something was wrong. He measured galaxy speeds in the Coma cluster, incredibly high. The cluster should have flown apart. Visible gravity wasn't enough. Zwicky called it dunkle materie, dark matter. His work was ignored for decades, but it was an early vote for an invisible universe. Then came the baby picture of the universe, the cosmic microwave background. Satellites like WMAP and Planck mapped this ancient light. Tiny temperature fluctuations are the seeds of structure. Studying those patterns reveals the universe's ingredients. About 5% ordinary matter, 27% dark matter. The CMB provides a cosmic recipe. Dark matter is a key ingredient. The overwhelming evidence for dark matter sent scientists on a cosmic scavenger hunt. If this stuff is everywhere, what is it? The simplest idea was that it was just ordinary matter that we couldn't see. Maybe it was made of things like dim brown dwarfs, cold neutron stars, isolated black holes. These objects, collectively known as machos, massive astrophysical compact halo objects, would have gravity but emit very little light. For a time, this seemed like a pretty plausible solution. It didn't require inventing any new particles, it just meant our universe could be filled with faint, hard-to-detect objects made of the same protons, neutrons, electrons we are. However, several large-scale searches designed to find machos came up mostly empty. These surveys looked for gravitational lensing events. While they did find some, they found nowhere near enough to account for the huge amount of dark matter required to hold galaxies together. Furthermore, our understanding of the Big Bang and the formation of the first elements places a very strict limit on the amount of ordinary baryonic matter that could have been created. The numbers just didn't add up. The universe simply doesn't contain enough ordinary matter. The ghost in the machine had to be something more exotic. With ordinary matter ruled out, physicists had to think outside the box. They turned to the world of particle physics. The leading candidates are called WIMPs, weakly interacting massive particles. These are hypothetical particles that are heavy, but barely interact with ordinary matter except through gravity. This would explain why we can't see them. Scientists are currently hunting for WIMPs in deep underground laboratories, hoping to catch the rare signal of a WIMP bouncing off an atomic nucleus. The discovery of dark matter was more than just the solution to a puzzle about spinning galaxies. It was a moment of profound humility for humanity. It was the realization that everything we have ever seen, every star, every galaxy, every planet, every person, is just a tiny fraction of what is actually out there. For thousands of years we've looked up at the night sky and thought we were seeing the universe. But we were wrong. We were seeing the cosmic foam on top of a vast invisible ocean. The luminous matter we cherish is just the decoration on a grand dark structure that governs the cosmos. This crisis completely redrew our map of the universe. We learned that galaxies are not isolated islands of stars but are embedded in immense spherical halos of dark matter. These halos are the true gravitational anchors of the cosmos. Without dark matter, galaxies as we know them would not exist. The gas clouds in the early universe would not have enough gravity to collapse. Dark matter is the silent architect, the invisible hand that sculpted the universe we live in today. It's the reason we're here. The quest to understand dark matter has pushed the boundaries of science and technology. It's a challenge that connects the largest structures in the universe with the smallest, most fundamental particles. So the next time you look up at the star-dusted arm of the Milky Way, remember what you're not seeing. Remember the ghost. The universe is not only more strange than we imagine, it is more strange than we can imagine.